Another common situation in calculus is the area problem. So last time we talked about the tangent line problem, like finding the equation of a tangent line by using limits to get that slope. So now we're going to talk about an area problem. So calculus was created to solve both of these problems, okay? And it was mathematicians were working on each of these, and they didn't really realize that they were connected to each other, and they are connected, okay? So they're actually kind of opposites of each other, but we'll talk about that throughout the year. So anyway, so it says, for instance, approximate the area under the curve y equals x squared between 1 and 3. All right, so if we're finding the area between 1 and 3, what we're trying to approximate is this area right in here, okay? All right, it says in order to do this, I choose several x values between these points. So I'm going to keep things simple. So let's choose x equals 1, 1.5, 2, 2.5, and 3. I don't want to do like 3.75 and all of those as well. All right, so let's do these values that I already have along the bottom. So it says draw a sketch of an underestimate and an overestimate. So if I'm trying to find the area, what we do is we basically, you could create trapezoids, you can create rectangles. We're going to do rectangles, okay? So if I'm doing an overestimate, well, let's do an underestimate first. I'm going to take all of these y values, and I'm just going to go straight over, like that. And I create these little rectangles. And each of these rectangles has an area. But it doesn't fill the entire space, right? It doesn't fill the entire, what we were talking about before. It doesn't fill all of this. Okay, so this is what we would call an underestimate. It's not the entire answer. All right, so I'm going to find the heights of each of these rectangles. So this first height has an x value of 1, and what would the y value there be? Can you guys tell? It's 1, right? We're basically plugging in to our function. Y equals x squared, we're plugging in 1, so we have the point 1, comma 1. When we plug in 1.5, we have 1.5, comma, do you guys know what it is? 2.25, exactly, because I'm plugging it into y equals x squared. If I plug in 2, I get 2, comma 4. If I plug in 2.5, 6.25, exactly. You good with your squares, Julie? All right, so if I talk about the area of this first rectangle, it's going to be the base times the height. Well, how big is this distance down here? Having trouble drawing it. Yeah, it's 0.5, right? So we're going to have 0.5 times 1. And then the next one's going to be 0.5 times 2.25. Does that make sense? And we're going to add all these together. So this is going to go under our underestimate. So we have 0.5 times a height of 1, 0.5 times a height of 2.25, 0.5 times a height of 4, and 0.5 times a height of 6.25. We what? Yeah, we don't use 9. Okay. Do you guys see why we don't use 9? Because that would be going this way, right? And that's not between 1 and 3. That would be past it. All right, so we find that value. So a lot of times I'll pull the 0.5 out since they all have that in common, and I'll find 1 plus 2.25 plus 4 plus 6.25. And then I take all of that and I multiply by 0.5. So tell me what you get when you do that. You guys have speedy fingers. Did you guys get 6.875? Is that right? Oh, nope, I forgot something. Hang on. .25. I did 2.5 on accident. 6.75. Did you guys get that? Okay. All right, so that's an underestimate. That's not quite filling the entire area. All right, now our overestimate. Well, let's think about how to do that, and I'll show it in a different color. So an overestimate, we want to cover the entire curve. Okay, we want to go over it. So instead, I'm going to use, we call these right-hand endpoints. Do you guys see why I would call it a right-hand endpoint? Because the rectangle is along the curve on the right side You guys see we use the point on the right and then we go straight over. The point on the right and we go straight over. So these are right-hand endpoints. So the underestimate used left-hand endpoints. How many rectangles did we have for the left hand? 4, right? So a lot of times I'll notate this as L sub 4. I think I do that on your homework as well. So meaning left-hand endpoints with 4 rectangles. So our overestimate is going to be right endpoints. So I'm going to use 4 rectangles again, R4. And now we're using different heights. So Ariana noticed that this point was 3,9. Now we're using the 9 for our height, the 6.25 for the height, the 4, and the 2.25. What is the height that I'm not using for the right-hand one? The 1, right? It's kind of like everything gets shifted over a little bit. So we're going to use those points. So I'm going to have 0.5 times 2.25. I'm going to have 0.5 times 4, 0.5 times 6.25, and 0.5 times 9. So for this one, we end up getting 10.75. All right, so what do you think we're going to do to get a better approximation? Yeah, AD, what do you think? Yeah, we're going to do the average. So if you average those two together, do I have that on the next page? Yeah, the average. We're going to do our 10.75 plus, what was it, 6.75, and we divide it by 2, and we end up getting 8.75. All right, and this is very, very close to the true area. So in calculus, in second semester, well, a little bit before second semester, we're going to start talking about how to find the area under a curve. The actual answer is 8 2/3. Okay, so even using just 4 rectangles, we got a pretty accurate answer, right? 8.6 repeating versus 8.75. Those are pretty darn close. All right, so what do you think happens as we have even more rectangles? It gets even more accurate because as you have closer and closer rectangles, right, there's less area that's being cut off. You can see how that works? So in the end, what we're going to do to find the area is we're going to take the limit as our number of rectangles goes to infinity. Does that make sense? And that would find the true area. All right, so what do you think happens when there are more rectangles? Your answer gets even closer. All right, so let's stop there.